A sudden eruption has shaken Mount Etna, but what emerged from the volcano this time has left scientists stunned. Amid the molten streams of lava, a strange, luminous material began to surface, unlike anything previously documented in the volcano's extensive eruptive history. The discovery has confounded experts, who admit the substance defies known volcanic behavior. As emergency teams rushed to investigate, early analyses confirmed the material did not match any recognized geological emissions on record. The unprecedented nature of the eruption has sparked growing concern. Could this be an entirely new volcanic phenomenon, or a signal of something far more dangerous forming deep beneath the Earth's crust? As unease spreads through local communities, researchers are in a race against time to interpret the volcano's newest and most cryptic warning. The eruption reached a terrifying crescendo earlier this week at 11:23 in the morning, local time, when Mount Etna unleashed a violent pyroclastic flow that tore down its eastern flank at a blistering 140.4 kilometers per hour. Composed of incandescent rock fragments, volcanic ash and poisonous gases, this searing avalanche of matter ignited panic as it raced downhill. Tourists and onlookers scrambled to flee, chased by a wall of fire and smoke. In just 60 seconds, the flow had travelled 2.34 kilometres, and by the time it finally came to rest 84 seconds later, it had burned a path stretching 3.26 kilometres, scorching an area roughly 2.64 square kilometres in size. Yet the term scorched belies the reality. The landscape had long been barren, repeatedly blackened by earlier lava flows that made plant life all but impossible. This extraordinary sequence followed an earlier eruption that began at approximately 5 o'clock in the morning, sending molten lava flowing roughly 2.7 kilometers across the rugged terrain over the course of 7 hours. Footage captured online revealed faint traces of white volcanic gas rising from the leading edge, a clear sign that at least 4 distinct lava lobes had emerged. The eruption unfolded within Valle del Bove, a vast chasm created by a catastrophic landslide around 7,200 BCE, when roughly 25 cubic kilometers of Mount Etna collapsed into the Mediterranean, sparking a massive tsunami. Today, that ancient wound serves as a natural lava basin, its steep slopes channeling new flows through treacherous pathways. The valley remains one of the most dangerous places on the volcano, with no official trails traversing its upper regions due to the persistent risk. Despite the chaos and alarming visuals that swept across social media, no casualties were reported. The closest groups of visitors remained at a safe distance, no closer than 0.8 kilometers from the edge of the pyroclastic surge, in zones where the threat had begun to lose momentum. What triggered this dramatic event was not a typical eruption, but a paroxysm, a brief yet ferocious explosive episode that interrupts Etna's more routine activity. Known for their sudden onset and destructive force, these violent bursts can take many forms, ranging from strombolian and Vulcanian eruptions to, in rare cases, the more devastating subplinian or Plinian types. This week's paroxysm produced one of the most extensive pyroclastic flows seen on Etna in at least 3.5 decades, a stark reminder of the volcano's unpredictable might. The latest eruption at Mount Etna has captivated scientists and observers alike, marked by a strikingly long pyroclastic flow in tandem with a strombolian eruption, an unusual pairing given that strombolian activity is rarely associated with pyroclastic surges. Yet under specific conditions, such flows can occur when a lava front or volcanic vent becomes excessively steep or structurally unstable, leading to collapse. In this instance, the pyroclastic flow exhibited a reddish-brown hue, suggesting a high concentration of scoria within the expelled material. While pinpointing the exact origin of the displaced crater, matters remain difficult. Preliminary assessments indicate it likely stemmed from a zone situated between the primary vent and a location roughly 250 meters to the north-northeast. The explosive phase that initiated this sequence began around 8 p.m. local time on June 1st, reaching a peak during the pyroclastic activity. Historically, Mount Etna has followed two potential paths after such paroxysmal events, either settling into a phase of reduced volcanic activity or unleashing another explosive episode within a short span of days. This duality reflects the volcano's inherent unpredictability, a trait that both unnerves and fascinates. While these eruptions pose significant hazards, they also unveil rare glimpses into the Earth's subterranean world. Each eruption becomes a geologic messenger, carrying material from the planet's inaccessible interior to the surface, allowing scientists to probe the deeper mysteries of Earth's composition and dynamics. Mount Etna, in particular, is a geological anomaly. Unlike other Italian volcanoes that are primarily products of the Ionian Sea's subduction beneath the mainland, Etna's origin story is written by a far more intricate convergence of tectonic forces. Geochemical investigations have revealed a hybrid signature in its lava, infused with both mantle-sourced elements like magnesium and iron, and crustal elements such as potassium. This unusual mixture points to a dual-origin magma source, drawing from deep within the mantle while also incorporating materials from the overlying crust. Such findings offer a rare opportunity to decode the mechanics of Earth's interior in real time. Volcanoes around the globe not only reshape landscapes but also conceal immense mineral wealth. Mount Erebus in Antarctica, one of the planet's most continuously active volcanoes, is believed to release up to 80 grams of gold into the atmosphere each day. Meanwhile, the ancient McDermott caldera, straddling Oregon and Nevada, harbors what may be the largest known lithium deposit on Earth, a resource crucial to modern energy technologies. These silent geological powerhouses are shaping more than just mountains. They are quietly influencing the direction of science, innovation, and the future of sustainable resource use. Volcanic eruptions are not simply dramatic spectacles, they are profound expressions of the planet's inner chemistry. Far beneath the surface, unimaginable heat and pressure fuse elements into complex minerals, which are then transported upward in surging currents of magma. As the eruption unfolds, this mixture, defined by variables such as temperature, pressure, surrounding rock types, and magma composition, deposits minerals that become part of the Earth's surface or vital resources for human civilization. These elements, forged in the crucible of the Earth, tell stories of ancient processes and ongoing transformation, making each eruption not only a moment of upheaval but also one of profound geological revelation. Silicate minerals serve as the fundamental building blocks of most volcanic rocks, forming the structural and chemical foundation of Earth's dynamic crust. Among the most significant are feldspar, olivine, pyroxene, amphiboly, and mica, each playing a unique role in the life cycle of volcanic activity and the transformation of landscapes. Feldspar, the most abundant group of minerals in the Earth's crust, are categorized into plagioclase and orthoclase. In volcanic settings, plagioclase is especially prevalent, commonly found in basaltic and andesitic lava flows, contributing essential elements such as sodium, calcium, potassium, and aluminum. Olivine, distinguished by its magnesium and iron-rich composition, is emblematic of basaltic lava typically erupted by shield volcanoes like those of the Hawaiian Islands. As magma begins to cool, olivine is among the first minerals to crystallize, forming distinct olive-green crystals. Although it weathers rapidly when exposed to surface conditions, the breakdown of olivine releases vital nutrients like magnesium and iron, enriching volcanic soils. Dark-hued and dense, pyroxene and amphiboly are groups of silicate minerals rich in iron and magnesium, commonly found in mafic and intermediate volcanic rocks. These minerals not only record the pressure and temperature conditions deep within magma chambers, but also contribute important elements to soils. Their presence offers geologists a window into the subterranean processes that precede volcanic eruptions. Mica, particularly biotite, appears in more silica-rich volcanic rocks such as rhyolite and dacite. Recognizable by their shiny, sheet-like structures, mica minerals break down to release potassium, a nutrient essential to plant metabolism. Their contribution, while less volumetric than feldspar or olivine, is nonetheless significant in shaping post-eruption environments. In addition to these silicates, oxide minerals such as magnetite and ilmenite are frequently expelled during eruptions, Rich in iron and titanium, these minerals hold both scientific and industrial value. Magnetite assists in interpreting the magnetic history of volcanic rocks, while both magnetite and ilmenite are economically important for steel manufacturing. Under specific conditions, particularly in the presence of volcanic gases and seawater interactions, sulfide minerals such as pyrite and chalcopyrite form. These sulfides often precipitate from hydrothermal fluids, accumulating into concentrated ore deposits, especially around submarine volcanic vents known as black smokers. These underwater systems are hotspots of mineralization and are key to understanding oceanic geochemistry and economic geology. Volcanoes also release a range of gases that later solidify into various minerals. Sulfur, often emitted as sulfur dioxide, can react with atmospheric oxygen and water to form sulfuric acid. This acid can in turn react with nearby rocks to generate minerals like gypsum or native sulfur. Although these gases can be hazardous to life, the minerals they form play essential roles in soil chemistry and the broader ecosystem, especially in nutrient cycling. Even volcanic ash, often regarded as little more than a disruptive byproduct of eruptions, has lasting geological and agricultural importance. Composed of fine shards of volcanic glass and minerals such as quartz, feldspar and zeolites, ash contributes significantly to long-term soil development. Its presence enhances soil texture, boosts water retention, and introduces a wide range of minerals that foster plant growth over time. Volcanic regions, particularly those along tectonically active zones like the Pacific Ring of Fire, are also repositories of trace but valuable elements such as gold, silver, and platinum group metals. Transported by hydrothermal fluids and concentrated over millennia, these precious metals form the backbone of major mining industries and are a testament to the enduring interplay between geological processes and human history. Each mineral released during a volcanic eruption contributes silently yet powerfully to the ongoing evolution of the planet. These substances not only alter the shape and texture of the Earth's surface, but also infuse it with the elements necessary for sustaining ecosystems and modern civilizations. Over time, volcanic minerals enrich soil fertility, support biodiversity, offer raw materials for critical industries, and provide clues about Earth's internal processes. Though born in searing depths and hurled outward with violent force, these minerals serve as the planet's subtle engineers, shaping life in ways often overlooked. Across the globe, certain volcanoes stand out not only for their geological intrigue but for the economic treasures they yield. Formed under conditions of immense pressure, heat and time, minerals such as diamonds, rubies, gold and platinum emerge from Earth's mantle or intricate hydrothermal networks, surfaces rarely touched except by the intense activity of volcanic conduits. An emblematic case is the Mirny mine in Siberia, Russia. While dormant today, it sits atop a prehistoric kimberlite pipe, a deep volcanic throat that once delivered diamond-rich magma to the surface. These diamonds, forged more than 150 kilometers beneath the crust, endure only because of their rapid ascent during ancient eruptions. This site, now one of the world's most productive diamond mines, has yielded stones prized both for their industrial strength and their unmatched clarity in jewelry. In northern Tanzania, Oldoinyo Lengai rises with a singular geological identity. It is the only known volcano to erupt nitrocarbonatite lava, a fluid, low-temperature form of lava composed mainly of sodium and potassium carbonates. Though visually unassuming, this lava carries a bounty of rare earth elements such as strontium, lanthanum and neodymium. These materials, essential for high-efficiency electronics, renewable energy systems and scientific instrumentation, highlight the volcano's understated yet profound contribution to the future of green technology. Kawah Ijen in East Java, Indonesia, offers a dramatic spectacle with its glowing blue flames and acidic crater lake, but its true value lies in the elemental sulfur extracted from its steaming vents. Here, miners work under extreme conditions to harvest sulfur of remarkable purity, a substance indispensable to agriculture, medicine, rubber production, and chemical industries. The volcano also emits lesser-known elements like selenium and arsenic, both of which are essential in metallurgy and electronic components. Deep in Ethiopia's Afar Depression, Ale maintains one of the planet's few persistent lava lakes, radiating heat from within a shifting tectonic rift. The surrounding terrain is rich in sodium carbonates, halite and potash, minerals born from the evaporation of volcanic brines. These resources are central to agriculture and industrial operations. Ale's setting, within an active rift zone where the Earth's crust is slowly pulling apart, suggests that even deeper and rarer mineral deposits may one day surface, unlocked by the forces of tectonic change. Together, these volcanoes illustrate how destructive energy can yield life-sustaining and economically vital materials, reminders that within Earth's most volatile places, its greatest treasures often lie hidden. Beneath the surface of Lihir Island in Papua New Guinea lies a colossal submarine volcanic system that anchors one of the most prolific epithermal gold deposits known to science. Here, the Lihir gold mine draws upon a geothermal engine forged by volcanic heat to extract vast quantities of gold from mineral-rich fluids circulating deep underground. The precious metal is often entangled with veins of pyrite and quartz, accompanied by trace elements such as tellurium and antimony, critical components in the advancement of semiconductors and solar energy technologies. Harnessing geothermal energy from the volcano itself, portions of the mine are powered sustainably, exemplifying how Earth's fiery depths can fuel both resource extraction and clean energy solutions. In the Caribbean, Montserrat's Soufriere Hills volcano has transformed from a looming hazard into a revelation of geological abundance. Since reawakening in 1995, it has reshaped the island with pyroclastic flows and towering ash clouds. Beneath this turbulent surface, hydrothermal zones have revealed concentrations of gold, silver and copper deposited by volcanic fluids as they migrate through fractures and faults. Though large-scale mining remains unfeasible due to persistent volcanic risk, the presence of these metals affirms the extraordinary mineral potential embedded within active volcanic landscapes. Iceland's Hekla volcano, once mythologized as a portal to the underworld, continues to produce andesitic to rhyolitic lava that contains trace minerals with profound scientific and industrial applications. Among them are zircon, thorium and zirconium-bearing compounds, materials used in radiometric dating, advanced ceramics and experimental nuclear technologies. In the geothermal field surrounding Hekla, volcanic heat drives the emergence of lithium and cesium-rich fluids, unlocking crucial ingredients for the rapidly expanding world of rechargeable batteries and energy storage systems. Further east, Japan's Aso caldera sprawls across the landscape as one of Earth's most formidable volcanic complexes. Active vents, seething fumaroles, and simmering hot springs emit volcanic gases laden with rare and technologically vital elements like tellurium, selenium and bismuth. These elements gradually accumulate within hydrothermal veins formed by the interaction of gases, fluids and rock, hinting at untapped reserves that may one day serve the electronics and renewable energy sectors. At the same time, the caldera's geothermal potential positions it as a key site for sustainable energy development. In the South Pacific, Fiji's Tuvalu volcano shelters an unusually rare form of gold deposit within an alkaline volcanic environment. The gold here is intimately associated with bismuthinite and stibnite, minerals enriched with bismuth and antimony, elements prized in everything from medical applications to flame retardants and next-generation batteries. The deposit is further distinguished by the exceptional purity of its gold and its alignment with quartz-bearing veins, making it a compact yet highly valuable site of geological interest and economic opportunity. Further south, in the frozen isolation of Antarctica, Mount Erebus stands as the most remote of these volcanic phenomena. Its icy flanks exhale plumes of volcanic gas that crystallize mid-air into exotic mineral forms like anorthoclase, bergedite, and sodium-rich feldspar. Though largely unreachable, Erebus functions as a natural crucible where intense heat and extreme cold converge, providing a unique glimpse into mineral formation in conditions that mirror those of distant celestial bodies. Its continuous activity and rare chemistry shed light on the dynamics of cryovolcanism, offering parallels to the icy moons of Jupiter and Saturn, where similar processes may be silently sculpting alien landscapes. These volcanoes are more than just tectonic powerhouses, they are elemental forges that shape the foundation of modern civilization. Their hidden veins and vaporous breath carry the raw ingredients of innovation, from the circuitry in smartphones to the silent propulsion of solar panels and electric cars. In their fury lies creativity, and in their depths the rarest treasures, evidence that the Earth in its most volatile expressions also serves as one of humanity's greatest benefactors. Mining directly into a lava crater or lake is far beyond the reach of current technological capabilities and remains an endeavor fraught with insurmountable danger. The temperatures within these molten pools soar between 1,000 degrees Celsius and 1,200 degrees Celsius, levels sufficient to obliterate even the most heat-resistant materials humanity has engineered. Under such conditions, machinery would disintegrate or seize almost immediately, and the mere act of approaching a lava lake would expose any living being or equipment to lethal levels of radiant heat and toxic emissions. The ground surrounding these fiery cauldrons is notoriously treacherous. What seems like solid terrain can suddenly collapse, as the ever-shifting magma channels beneath reshape the landscape without warning. This constant geological instability poses catastrophic risks not only to human life, but also to any machinery that might be deployed in the vicinity. Moreover, the atmosphere around lava lakes is thick with toxic gases, sulfur dioxide, carbon dioxide, hydrogen sulfide, and hydrochloric acid among them. These emissions are not just harmful but potentially fatal, capable of causing respiratory paralysis, chemical burns, or unconsciousness in mere moments. Designing systems robust enough to withstand these environmental extremes would require not just immense financial resources, but a level of engineering sophistication that does not yet exist. Robotic intervention has been tested, but even advanced drones and probes developed by leading institutions such as NASA fail to endure. These machines succumb rapidly to the blistering heat or are rendered inoperative by the corrosive gases. No existing robotic technology can survive long enough in a molten lava environment to make resource extraction feasible. Even if such a feat were possible, the economic rationale remains doubtful. While lava contains trace amounts of elements like iron, magnesium and titanium, these are uniformly distributed throughout the molten rock, not gathered in minimal concentrations. Valuable metals commonly associated with volcanic systems, such as copper, gold and silver, are typically deposited in solid hydrothermal veins that form deep below the surface or near cooler volcanic vents, where mineral-rich fluids have gradually cooled and precipitated. Despite these challenges, scientific exploration continues. Researchers collect samples of solidified lava and volcanic gases using remote tools and specialized drones, contributing to a deeper understanding of volcanic behavior. While speculative visions of AI-guided robots and ultra-durable materials adapted from space exploration persist in academic discussions, these ideas remain distant possibilities rather than near-term solutions. For now, the heart of an active volcano remains one of Earth's most hostile frontiers, untouchable, mesmerizing, and profoundly humbling. If you enjoyed this deep dive into volcanic wonders, don't forget to like, share and subscribe to the channel for more fascinating explorations. Hit the notification bell so you never miss an episode. Got a favorite volcano or a burning question about Earth science? Drop it in the comments, we'd love to hear from you. Until next time, stay curious and stay grounded.